All right, we are back and we're still talking about roots and zeros. So maybe you saw that. I could at least see it. That was important. Roots and zeros out of 5, 7. And I said we were going to pick up in the second section about talking about Descartes' rule of signs. This is really going to be one that's going to help you figure out what types of roots you're looking for to help eliminate whole groups of numbers and help narrow down your thinking as you're working. So this is going to be important. Now, as we look at the verbiage of it, you might go, okay, that doesn't make sense. Well, exactly what we're talking about. Bear with me. We will get there, and we're going to do an example where I think it's going to make a lot more sense when you see what's happening. Really, what René Descartes figured out was if you have a polynomial with real coefficients, so what we're used to seeing for polynomials, the same kind of problems we've been looking at, and it's arranged in descending powers of the variable. So we've got to go from biggest power to least power. Then the number of positive real zeros is the same as the number of changes in the sign of the coefficients terms, or less than that by an even number. Okay, so that means you're plugging in a positive x, and however many times it changes signs, it'll be that amount of positive real roots or positive real zeros, or an even number less. So if there's 4 sign changes, there'll be 4 positive real zeros, or 2, or maybe none. Now, let's say instead you wanted the number of negative real zeros. If you would go and plug in a negative number, then you have the negative real zeros is the same as the number of changes in sign of the coefficients of the terms, or less than that by an even number again. And just remember, like we talked about in the previous video, imaginary roots come in pairs. So really what Descartes' rule of signs allows us to figure out are the combinations of types of roots that we could have between positive real zeros, negative real zeros, and imaginaries. And what we'll ultimately do is we're going to make a chart to help keep us organized with all of that. And I think that will help make this all make sense. So let's take a look at an example. And this will hopefully make more sense. So we have to state the number of positive real zeros, negative real zeros, and imaginary zeros for this function. 4x to the fourth minus 3x cubed minus x squared plus 2x minus 5. Okay, so the first thing that we know is it's a 4th degree equation, correct? It's a 4th degree function. Everything's in descending order, so we know there's going to be 4 zeros. Not any more than that. Now, let's take a look. So our initial function here is considering that we have a positive number plugged in. So does the sign change as we go from the first term to the second term? We go from here to here? Yes, it does. This is positive. This is negative. It takes the sign with it. Now we go from the second term to the third term. Nope, it does not. Negative, negative. Now we go negative to positive. That's a change. It doesn't matter whether it's going positive to negative or negative to positive. Just is it changing? And yes, it is. And then here we go positive to negative again. So that's a yes. So there are 3 sign changes, which means there are either 3 or 1 positive real zeros. Remember I said it's the number you've got or an even number less than that. So what's 3 minus 2? It's 1. So let's keep that in mind. And in fact, what we're going to do is we're going to start ourselves a little chart down here at the bottom. And we're going to make a spot that says for positive real zeros, negative, imaginary ones, and then our total. So it looks like I just misspelled pint. Don't spell it pint because you actually want to go positive, negatives, imaginary, total. So we know we have some options. We could have 3 positives We could have one positive. Now, what happens? We said imaginaries come in pairs. So if I have 3 positives and I can have a total of 4, I can't have any imaginaries, can I? Which means there could be one negative. So 3 plus 1 plus 0 equals 4. Okay, if I have one positive real, I could possibly have 2 imaginary. So we don't know how to fill this spot in yet. We've got to go take a look at the negative version of, or negative side of this. So let's say I plugged in a negative number. I'm going to go plug in a negative number into the equation. When I do that, I've got to simplify things first. So I take a negative to even power, it makes it positive again. So nothing changes with the sign. I take a negative to an odd power, that stays negative. So now my negative 3 times negative x cubed becomes plus 3x cubed. Negative x to squared is still keeps it positive. That sign doesn't change. Plus 2 times negative x becomes minus 2x, and then minus 5, nothing changes. So let's look. We're going first to second term, no change. Second to third, no change. Third to fourth, yep, there's a change. Fourth to fifth, no change. So that means there's only one negative real root. That's the only possibility. So now we can fill that in our chart. Well, we filled it in the first row because we already knew it. There had to be at least one. But now we can fill this in here and say, okay, I've got one negative, one positive, means I have to have 2 imaginary to have a total of 4. Now, if you have other options with the with the negatives, then you've got to continue on your chart. But you see how this chart helps you organize, and right away we could figure out that one scenario we're going to have no imaginary numbers. Now, for right now, all we're going to do is this. We're not going to solve yet. I want to get you guys familiar with using this before we use it to help us solve. So let's take a look at a couple more examples here. All right, state the possible number of positive real zeros, negative real zeros, and imaginary zeros for each function. Let's start by, I'm going to scoot that up all the way, okay? And let's start by making our little chart down here. Positive, negative, imaginary, and total. Now, as we go, if you don't want to sit there and add up all the numbers like we did and just, show all that adding, you definitely don't have to. I just like to show what we're doing to get that total. All right, so first, let's look at the equation as it is. How many roots are we going to have total? 3 roots. So we know down here we're going to have to total 3. Let's see how many more times we have to write it. So let's look. First term to second term. Is there a sign change? No. Second to third? You bet. And third to fourth? No. So this means there's one positive root. So I'm going to put 1 in there. Now, what do we say? You have to have... the imaginaries have to come in pairs. So it is possible that we could have no imaginary, or we could have 2 imaginary. So let's see how our scenario is going to play out. This is one of those times where we can't fill in a whole lot yet. We got to see what happens with the negative. So now watch what happens if we have a negative. Where the power goes on the outside. -12. Okay, so we simplify. This now becomes a negative 3x cubed, right? Still stays plus x squared, becomes plus 8x and minus 12. So this is the positive scenario, this is the negative scenario. Okay, first to second, yes. Second to third, no. Third to fourth, yes. that means there's either going to be 2 or 0 negative roots. Remember, we can go down by an even amount. So 0 is a feasible option. So that means now for our negatives, we can say we have 2 or we can have 0, but we know we're going to have 1 positive for sure. So if I have 1 positive, 2 negatives, no imaginary because we have to total 3. 1 plus 2 plus 0 is 3. I have 1 positive, no negative. It means I have to have 2 imaginary to get me a total of 3. Whatever number you write in your total column should match the highest power of your equation and should always be the same. So this would be your answer at this point to say these are the possible combinations of roots. All right, let's do one more example. Number 5. So are our terms in descending order? Yes, they are. Do we need to worry about that we have no x term in here? We do not. Here it does not matter. All right, how many total roots are we going to have? Hopefully you said 5 based on that. Then we're going to have 5 roots. So let's start ourselves a little chart. Use your space wisely, of course. Positive, negative, imaginary, and total. So let's look at the positive scenario. First to second, yes, there's a sign change, positive to negative. Second to third, nope. Third to fourth, yes. And fourth to fifth, yes. So we have a possibility of positives of 3 or 1. Now, remember, we got to total 5. Now, I intentionally left a little space there. Let's go figure out the negatives. If it helps, if you want to write 3, some people like to write this down. 3 or 1 positive. Now, let's see what happens when we plug in a negative. 3 times x to the negative x to the 5th minus negative x to the 4th minus negative x cubed plus 6 negative x squared minus 5. All right, so if it's an odd power, it has now switched signs. If it's even, it has remained the same. All right, let's take a look. Negative scenario. First to second, sign change? Nope. Second to third? Yep. Third to fourth? Nope. Fourth to fifth? Yep. So negatives, there's 2 or 0, which means now we have multiple scenarios, right? Negatives could be 2 or 0. So we're going to end up with, so we have 2 or 0 negative, that helps. We could have 3 positive, 2 negative, and no imaginary. We could still have 3 positive, no negative, and 2 imaginary. 1 positive, 2 negative, and 2 imaginary. Or 1 positive, no negative, or imaginary. Notice we need to set up all the different scenarios here. So that's why it's important to figure out the negative possibilities. And if you had wanted to, you could have also done this like 3-1, 3-1. And that would have been fine as well. Some people like to do that. They write down the 2 possible positives first, and then if they have to repeat it again, they will. That's all. That works. I'm not that picky. But the idea is now we see all of our possible combinations. So that when we would move forward and solve, we start to be able to say, oh, I have a positive root. Okay, this is good. If I come up with a negative, then I know I'm done with my positives. If I can't come up with a negative, then I probably need to find some more positives. It just helps you start to try and organize things a little bit more. And so that's what you're going to be practicing with Descartes' rule of signs.